Welcome to Shri Learning Academy. Let's simplify types of schedulers. In our previous video, we looked at the big picture of process scheduling. Now that you've mastered the basics, it's time to level up and look at the actual managers, the specific schedulers that make these high-level decisions happen behind the scenes. These schedulers work at different levels and different times. Together, they make sure the system runs smoothly, does not overload itself, and feels responsive to the user. To understand types of schedulers, it helps to imagine a busy airport. Not every passenger is allowed directly onto a plane. First, passengers enter the airport, then they wait in different areas, and finally they board the plane when it is their turn. In a similar way, processes do not jump straight onto the CPU. They pass through stages, and at each stage, a different scheduler may be involved. Let us start with the long-term scheduler. This scheduler decides which processes are allowed to enter the system in the first place. Think back to the idea of a job pool, which we briefly touch upon when discussing process scheduling. The job pool is a collection of all programs that are waiting to be executed. The long-term scheduler picks some of these programs and loads them into memory so that they can become active processes. The key role of the long-term scheduler is control. It controls how many processes exist in the system at any given time. This is important because memory and CPU resources are limited. If too many processes are loaded at once, the system may slow down or even become unstable. If too few are loaded, the CPU might sit idle, wasting time. For example, imagine a batch system where hundreds of jobs are submitted by users. The long-term scheduler might only allow a few jobs into memory at a time. It looks at the nature of the jobs and tries to maintain a good balance between CPU-bound processes and IO-bound processes. CPU-bound processes mainly use the processor for calculations, while IO-bound processes spend more time waiting for input or output. If the system only loads CPU-bound processes, IO devices may remain idle. If it only loads IO-bound processes, the CPU may not be fully used. By choosing a mix, the long-term scheduler improves overall system performance. In modern time sharing systems, the long-term scheduler may not be very active or may even be minimal. This is because users expect programs to start quickly. Still, the concept exists, especially in servers and large systems where workload control is critical. Once a process has been admitted into memory, it is ready to compete for the CPU. This is where the short-term scheduler comes in. The short-term scheduler is the most active of all schedulers. It makes decisions very frequently, sometimes thousands of times per second. Its job is simple in description but complex in execution. It selects one of the ready processes and assigns the CPU to it. You can think of the short-term scheduler as a traffic police officer at a busy intersection. Cars are already on the road and ready to move. The officer decides which car goes next and for how long. In operating systems, the ready queue holds processes that are ready to run but waiting for the CPU. The short-term scheduler picks one process from this queue based on a scheduling algorithm, such as first come first serve, shortest job first, or round robin, which we will study in detail later. For example, in a multitasking operating system, you might be listening to music, browsing the web, and downloading a file at the same time. All these activities are handled by different processes. The short-term scheduler rapidly switches the CPU among them. Each process gets a small time slice, creating the illusion that everything is running at once. This frequent switching is closely tied to context switching, which we will cover next, where the CPU state of one process is saved and another is restored. The short-term scheduler must be extremely fast. Any delay here directly affects system responsiveness. That is why its logic is kept efficient and it operates mostly in kernel mode, as discussed earlier when we talked about OS architecture. Now let us move to the medium-term scheduler, which is often less talked about but plays a very practical role. The medium-term scheduler focuses on managing memory and system load by temporarily removing processes from memory and bringing them back later. This process is known as swapping. Imagine a situation where too many processes are in memory and the system starts slowing down. Instead of completely rejecting new processes, the operating system may decide to suspend some existing ones. The medium term scheduler chooses which processes to suspend. These suspended processes are moved out of main memory to secondary storage, such as disk. Later, when the system load reduces, they can be brought back into memory and resumed. A simple example would be a system running many background applications. Some of these applications may not be needed immediately. The medium term scheduler can suspend them, freeing memory for more important or active processes. When you switch back to one of those background applications, it is resumed, often without you even noticing what happened behind the scenes. The medium term scheduler helps improve the degree of multiprogramming in a controlled way. It also plays a role in avoiding a situation where the system spends more time swapping than executing useful work, which relates to the concept of thrashing that we will explore later in memory management. It is important to understand that not all operating systems clearly separate these three schedulers as independent modules. In many modern systems, their responsibilities overlap or are implemented together. Still, conceptually, separating them helps us understand how the operating system manages processes at different levels. To summarize the flow in a simple way, the long term scheduler decides which jobs enter the system. The medium term scheduler decides which processes stay in memory and which ones take a temporary break. The short term scheduler decides which ready process gets the CPU right now. Each scheduler operates at a different time scale. The long term scheduler works slowly, the medium term scheduler works occasionally, and the short term scheduler works very frequently. By dividing scheduling responsibilities this way, the operating system achieves better control, efficiency, and responsiveness. This layered decision making is one of the reasons modern operating systems can handle so many tasks smoothly without the user having to worry about what is happening internally. That is it for this video. See you in the next one.